So now there is a talk by Frank Rosmej about the principles of non-Maxwellian and non-stationary atomic kinetics driven by suprathermal electrons.
Yeah, I want to report about some investigations concerning the kinetics that is perturbed by suprathermal electrons and or intense photon sources. So let us start with the introduction concerning standard charge state distribution. So you have the charge state Z, Z plus 1 and Z minus 1, and they are connected to each other by ionizations, free body recombination, radiative recombination, in particular also to dielectronic recombination. There are other processes like charge exchange, etc., that could be added here. So the stationary solution is given by this expression. So that is the ratio of the ionization rate to all the recombination rate and maybe also charge exchange. And that is the corresponding simulations, which is a standard picture that, for example, that you see well the broad shell structure. So that is 1s2 configuration, that is a 2p6 configuration. So you need a lot of more energy to make the ionization from these charge states. So what is particularly interesting is that if you compare many codes, they almost all well agree with the standard picture. But if you add suprathermal electrons in the calculation, then the differences are considerably. So we started to study that more seriously. And let us look at only this part where the helium-like charge state is dominant. So here you have the hydrogen-like charge state, lithium-like, beryllium-like. And now if you add suprathermal electrons, that of course results into enhanced ionization, and that is a trivial change. Yeah, you enhance the ionization rate, so you enhance the Z bar. But you can also see what is a non-trivial change that is connected with a qualitative distortion of the charge state distribution. For example, in blue, that is a Maxwellian case. In red, the non-Maxwellian. You see, for the helium-like, you have slight changes. So that would be difficult to diagnose with some emission lines, which have additional noise, etc. The same for the lithium-like, beryllium-like, there's some changes. But you see that there is a large difference, for example, for the hydrogen-like. So you see, and that is what is meant, there is a qualitative change in the charge state distribution. And the point is, if you want to validate some simulations, you need to make an experiment that is sensitive to these qualitative changes. Why that is not so trivial? Because usually if you determine the temperature for some elements or for some situation, you take, for example, a hydrogen-like line or helium-like line, you make the ratio, and the ratio, of course, increases with the temperature because ionization is going on. Excitation energy of these two lines is almost the same. Now, if you add suprathermal electrons, you have likewise a situation that, for example, for a low bulk temperature, you can also have a high ratio, and that is driven by the suprathermal electrons. So that means that if you use such kind of mapping for the experimental results, then you have always the problem that you do not really know, is it the Maxwellian high temperature case, or is it the non-Maxwellian low temperature plus suprathermal electrons? And that is not related to this particular charge state and this particular transition. This is a general feature of the asymptotics of cross-section, so that concerns almost all diagnostics. Similar problems exist for density diagnostics and so on, because it's also related to the principles of the exchange cross-sections. So the question is how you can map these qualitative changes. You can say, okay, I look at the hydrogen-like series, helium-like, and then I look at the lithium-like, but you see, for example, that's a calculation for titanium. Then you have about 2 angstrom in the K shell, 15 angstrom in the L shell, and that means two different spectrometers. That would be a mess to calibrate that to each other. But you can find a situation where all these charge states are readily available in a series, and that is concerned with the inner shell excitation lines from the autonizing states, which configuration is given here. So the hydrogen-like is in 2.5 angstrom, the lithium-like 2.6. So all that is very close. And if you do that in the simulation, what you see, that is a Maxwellian high temperature case. You see the hydrogen-like, the helium-like, and the low temperature case, you see the beryllium-like, bohr-like, carbon-like, and you see the wavelength. All that is very close. So that is one X-ray spectrometer. And then you see in the case of non-Maxwellian plasma, you have observed, or you can observe this mixture. You see hydrogen-like represented by the Lyman alpha, and the lower charge state, lithium, beryllium, and bohr, due to this so-called dielectronic satellites from these autonizing configurations. And that was tested that it works in a laser produced plasma experiment. So that is the time evolution of this experiment. In black, that is the experimental observation. And in blue, that is the simulations. And the simulations are very complex because they were done with an algorithm that generates test functions to find out what is a fraction and what is a temporal evolution of the parameters. So you see here, that is almost a low temperature case. And then you see exactly here this characteristic case. You observe simultaneously Lyman alpha and the low charge state, which corresponds exactly to this case for the qualitative changes. And independent of the validation of these simulations, if you are able by test function procedure to obtain the time evolution of the suprathermal electron fraction, you can go a next step further, for example, to identify some sort of instability mechanism, and that is depicted here. That was, for example, additional measurement of the stimulated Raman scattering losses, and that coincided with the determination from the spectroscopic results. In any case, if you have, for example, suprathermal electron impact, if you have perturbation by intense photon sources, then you are never really in a stationary case. So you have always a sort of time evolution. And then the situation becomes very complex. And the question is, can you derive some general characteristics that permit you to eliminate some sort of uncertainties in order to avoid that you rely on very complex simulations, which you really do not understand in the detail from the final outcome. So for that purpose, let us look just a two-level atom, charge state Z and Z+1. They are linked by ionization and the recombination process. And let's consider the rapid cooling of a plasma cloud. For the two-level atom, that means all is in the higher charge state. So the probability for Z+1 is 1, and the lower charge state is 0. And now you can solve this differential equation in an analytical way, and you find a solution. It is man minus this exponential function, and that has a well interpretation. So at small times, the charge state Z grows linear, and at large times, it goes evidently to a saturation. So all is in the charge state Z. And in between, there is a characteristic time scale because there is this exponential function. And the characteristic time scale is given by the sum of ionization and all recombination processes, and not only by the characteristic time scale either of ionization or recombination. It is both which determine this time scale. So let us assume for a moment that three-body recombination is negligible. And in that case, you see that this characteristic time scale is a function of temperature only. And then you can extract the 1 over NE, multiplied on the left side, and you have a product of density and time. And this has the physical meaning of a confinement parameter. And if you really do the numerical simulations, you will find out that almost independently of any element, almost independently of this three-body recombination, there is a characteristic confinement parameter, for example, for the K shell, and you can do that for any other shell, of about this value 3 times 10 to 11. So it looks like a sort of Lawson criteria, but it is a confinement parameter for atomic physics processes for the evolution of the system. For example, if you put in 10 to 6 for a plasma, then that means you need about 3.5 days to equilibrate your cloud. And if the time available is larger than this time, then you have only then you have the quasi-stationary situation. That means the system is following after some time gradually temperature and density changes if these changes are lower than this relation. What happens if, for example, the ionization is very rapid? For example, if there's a rapid burst of photons and it acts, for example, on a solid, on ice, or something else. In that case, it looks that you have a very complex simulation, which is really the case, and that was really done here. That is a complex simulation from the solid, which is irradiated by a strong burst of photons. Then the solid starts to ionize and goes through all the charge stages. And can there be detected some general features? Why that is important? Because the chemical properties, the thermodynamic properties, for example, if you have the ice and you ionize it, you have the ionization potential reduction, and all that depends on the mean charge states, for example. And now you need to know all the distribution of this charge state to calculate this parameter. And firstly, we find out by numerical simulation, there is a sort of shock behavior in a sense, not in a hydrodynamic sense, but in a sense of atomic physics process. And that is seen here. For example, in red, that is the average charge state, which is calculated exactly from the simulation. And here you see, for example, the maximum of the charge state 6 plus, yeah, that is the case for solid aluminum. And you see that when at this time the charge state 6 plus has a maximum, the average charge state is very close to 6. And you can look at that for every other charge state. So that means at the time where the respective charge state has a maximum, it corresponds approximately, not exactly, but approximately to the mean charge state. So that means that you have this relation. That means in a rapidly shocked system by burst of photons and even by suprathermal electrons, you have this relation, and you can really reliably determine your other properties in order to make right your kinetics. And it appears that just this observation turns out to be theoretically very challenges, because there are, as you know, many codes on the market which can calculate the charge states also with suprathermal electrons. And the point is that most of them represented, for example, by this very famous and available code fly-chick. You see that if you calculate the case of suprathermal electrons, you see that the higher charge states which are experimentally observed, they're completely absent. And the reason is not clear. So we try to develop our own simulations. They are shown on the right side. And here you see it looks that our simulations, they do a better job. This is an observation limit. So we see charge states unto lithium-like and really helium-like, although that is not exactly matching in the moment the experiment, but it looks very promising and much better what is available in the standard calculations. And what could be the possible reason? that is probably connected with the phenomena of dielectronic recombination from excited states and maybe a wrong or right coupling of the different channels of the excited states. And the point is that you cannot make an experiment at the synchrotron or low density source because there you don't have the excited states which you want to test, because you cannot sufficiently populate them in a low density plasma. So you need necessary to do that probably with a laser experiment. So conclusion and outlook. So we have observed charge state distribution in femtosecond laser produced plasma, which is in discrepancy to almost all standard calculations available. That challenges state-of-the-art non-Maxwellian atomic kinetics, which is by no means well established. The point that characteristic timescales exist in atomic physics allows you to make some clever analysis of the experimental data, how you want to test, for example, a burst of photons. That you can, for example, do with the X-ray free electron laser. And that is a sudden burst of maybe some tens of femtosecond photons in a certain range. Experimentally, you need to couple X-ray spectroscopy by CCD, single photon counting, to observe all these charge states, and to finally make an analysis of the suprathermal electrons and the intense photon sources. Thank you.
Thank you very much. So there are some questions by Patrice Telet. What's the density interval range you are measuring?
For the laser produced plasma, it is in the range of 10 to 20, 10 to 21. And if you add the very early part of the femtosecond laser, for example, shown in this simulation, for example, in this part for the free electron laser, that is solid density. Yeah, for example, here you interact with the solid density, stay at near solid density, and only here you have some expansion. So almost that is near solid density and becomes here hot plasma with a few hundred electron volts.
Okay. There is a second question by Patrice. What are the experimental limitations to high Z spectroscopy?
The experimental limitation was some years ago that you do not have the intense photon source. But now there are many installations, for example, in the United States, in Hamburg, or in Japan, the SACLA, the UFL, or the LCLS, data available since a few years. So you have now, since a few years also, the experimental station to combine the XFEL with a powerful laser. So since only a few years, somehow you are well equipped to make such kind of experiments which have not been possible before. And you really need an XFL. You can say, okay, I have a synchrotron. I also have the photon source. That is true, but the synchrotron has too low intensity. So if you hit with a synchrotron the solid, that means the defect, the hole, is a rare occasion. You never hit that as a plasma. And you need to have a so intense photon source that the hole is practically in every atom. And in that case, you have the regime which you want. And only since a few years that is available with the XFR.
Okay. Well, thank you very much. I think we'll close this session.